in the lab named Brain Dynamics Lab. And the reason being, sorry, yeah, the reason being that, especially in the psychiatric population, we are hoping that by looking at the brain dynamics, can we find a biomarker in the state transitions for like ruminative tendency, the slow dynamics versus attention deficiency, which I'm suffering from for sure, fast dynamics. And the hope is to use different methods to basically go there. So here comes TDA. This is one of many approaches. I'm sure that many exist. And I was fortunate to be mentored by Gunnar Carlson, who is kind of considered a father of this field in applied topology and how they applied it to the data sets. And two main, so the idea of TDA is that if you're sampling a bunch of data points, and then what it wants to know is that the shape is a loop, essentially. Not a big deal. So if it's a 2D data, you can capture the shape. But now imagine if you have thousands of dimensions, and how can you still capture the shape of the? The hope is once we get the shape, we can know a lot more about the data. There are two main approaches. One is called Mapper, and this is where I'll spend most of the time. Where the idea is, again, if you have a 2D structure like a circle, how can you end up creating a shape which looks like a loop? But there are two benefits of creating that kind of loop. One is the shape. The second is it's a graph. When you have a network, then you can study the heck out of the network properties, the topological properties, and make sense with that. And I'll go in detail exactly how to do. The other one, just like a teaser, called persistent homology. And the idea here is that, again, similar idea that you want to capture the shape, but the keyword is persistent. So we really want to know what shape persists over different values. So I didn't want to play this already, but imagine you have like a functional connectivity matrix, region by region. And obviously it's like weighted with different correlation values. And now I tell you, okay, go from correlation value, like threshold this matrix at different values of R from 0 to 1. And then you want to know, are there, across so imagine this range is like not 1 to 3, but like 0 and 1, like a correlation matrix. And you're kind of saying, as I change the threshold for the correlation matrix, which connections are still available across most of the threshold value, right? That's something you probably have done in graph theory or some other space, but that's typically we do as a pairwise. And now the idea is, can we do many body interactions, meaning can you find one-dimensional holes, two-dimensional holes, and higher dimensional holes? And that's the idea of persistence. So what persists across multiple thresholding? So that really helps with noise, filtering out noise and stuff like that. So here is just showing again the example, and this is like a visualization. Check out the YouTube by Matthew on it. But so the idea again is you take each point and you literally just blow it up like a balloon. And that's the parameter D, the radius of the circle at each point. So as I keep on blowing up these balloons, at some point they will start colliding. And the minute they collide, that's like a connection, right? That's one way to think of it. And you keep going. Eventually, cycles are forming now, smaller cycles. And at one point, the bigger cycle will appear. And this big cycle kind of stay there the longest. And we keep on, eventually it'll die. So this is like birth and death kind of stuff, really cool analysis. So the thing that lives the longest is the winner, and that's the person. Here it's just, it could be anything at any 2D embedding of any data. It's a 2D embedding of anything. Okay, so let's go to Mapper. Mapper is more fun in the sense that it's, so in persistent homology, you get very cool signal that persists, but it's not easy to interpret them. And I'm happy to talk about it later, but it's still cool math behind it. It's much more stable, I guess, than Mapper. The cool thing about Mapper is that it gives you a graph at the end of the day, like a network, but also it compresses the data. So let me just take an example of this 3D trefoil knot, and that's also in the tutorial. So you will get to see each stage of Mapper in the notebook. So this 3D trefoil knot is, what's the shape of this object is a closed loop. So if an ant It's apparently a famous object in maths. Many maths people love it. But if you start walking on it, you will never fall off. Right? It's a closed loop. That's the property of it. And the point is, can we capture that shape in lower dimension than 3? So essentially 2, right? So this is what you typically do in any dimensionality reduction. You go from 3 to 2 dimension. Here I simply just got rid of z dimension. I say only x and y. You get this kind of a contour. And then how do we get that information that we lost because of this projection? So the way Mapper tries to do it is you bin this entire space whichever was your lower dimensional space. You bin it, and there are like gazillion ways to bin it. That's where the parameter optimization comes in. Simplest way is just to bin it squares if it's a 2D space, but they're overlapping squares. And so then what we then do is, let's say we go within each bin. So let's say you look at this bin guy. And here, even though all the blue and red and green don't look separable, so there's a hack there. What we do is we say, okay, within each bin, we're going to go to the high dimensional space and see where these points were in the high dimensional space, and then bring that information back to the low dimensional space. So we're in a way hacking or sneaking high dimensional information back in the low dimensional embedding. We then cluster these points within the bin. So we know the green is far away within this bin, green is far away, and blue and red are closer to each other. So you keep green farther apart and blue and red much more closer to each other, and you cluster them, blue and red together, green far away.
It's a filter which overlap.
Filter, you can call it a filter, perhaps, yeah, but the idea is that you are preserving the local structure of the data, and you don't care about the global information.
If you bring this, you still need to back to the original data.
Yeah. So it's inversion. It's called filter inversion.
So it seems like overall it's a 2D, but at some points or some area it's 3D.
So the original data was 3D, right? And so the shape of that original data is a closed loop. But when you reduce it to lower dimension, then you lost that information. And there could be other shapes that you also lose. So how do you sneak in the information that you have lost in the high dimensional space, but bring it to the low dimensional space? So the one way to do it is do this partial clustering, as we call it, where you divide the space into bins. Within each bin, you cluster the data in a way that preserves the high dimensional information, but only for that bin.
Cluster is still 2 dimension.
Dimension. No, you're just clustering points. You're still in 2D. You're not going in 3D. It's not like tiny 3D bubbles popping up. Still in 2D still. And then based on this binning parameter, like how many bins you make, this is a typical cluster, any kind of clustering. So if you have only one bin, then everything's connected to everything. If you have gazillion bins, then nothing is connected to anything. And then this is a parameter you vary. And the idea is that anytime 2 bins share a data point, you connect them by an edge. That's how this is what I was talking about earlier when I think somebody asked the question that edges represent similarity, but lesser degree similarity, whereas nodes represent higher degree of similarity. So the cool thing then is as compared to, let's say, TSNE or PCA, which kind of, you can think of them as like the first step of Mapper. You don't get the information, whereas in Mapper can retrieve it, because this is essentially a necklace. So if you pull the bead, you get the shape that it's a 2D. Okay. But the question about TSNE, UMAP, you can use them, and in the notebook, I think you're using TSNE. So you can use them as a first step, and then kind of compress information more and sneak in information more from high dimensional space. Any dimensionality reduction is good. We personally love ISOMAP. Does a great job with fMRI data. But that was one of my pitches, like to try different things, and I guess nobody liked it. Okay. So then we very briefly applied it to fMRI data. This is the original application, this 4D data. And then you can kind of roll it out as time versus voxels. So here we were trying to be, sorry, I bragged too much. So we kept it at 270,000 voxels. You don't have to be. Parcellation does pretty much a good job as well. So again, 4 steps. You reduce the dimensionality But each node here is any one row, meaning the entire brain activity at any one time point. In this case, you can do whatever masking you like. If you, I don't know, again, in the tutorial, we have Haxby's data, Jim Haxby's science paper data. So there, I think we are focusing only on ventrotemporal cortex or something. So you can mask the data however you want in the column space. And then you do binning and partial clustering and create a graph out of it. And the idea again is that these nodes, the size of the nodes can tell you which TRs are represented by it. So they're highly, highly similar. They kind of coalesce and create a bigger node, bigger size node. So the data initially we applied this on is continuous multitask paradigm where people did 4 different tasks in blocks of 3 minutes each. And we wanted to first see whether this thing will actually work on it. And the reason we like this data set because it has ground truth about transitions. We know exactly when you switch a task. And then we also have behavior. So we wanted to know whether it can pick up individual differences in behavior. So again, everything is done at a single person level. You get a graph like this. But the beauty of Mapper comes in from the fact that you can then color these graphs based on whatever information you have. So meta information here is again different tasks at each TR that they were doing. And you get this pretty spider chart where again the nodes and the proportion of nodes tell you how many TRs come from which task, basically. So we found that whenever people were doing cognitively effortful tasks, then those things were part of the core because the spatial activation patterns were much similar. Versus mind wandering was always like these excursions, and they come out and then come back, and then video was the same way because they were watching an aquarium, and every time a fish jumps or something, they had to press a button. So it's very much like resting state. So one of them, I think I did this already, right? So one of the subjects is the best performer, one of them is the worst performer. Any guesses? 2 things left is the best performer. Okay, who thinks right is the best performer? Why you guys? Why? So why is right the best?
I was just thinking there might be more separation. So it's like,
yeah. Very, very good. That's exactly what we found. So again, that person was sleeping inside this kind. No matter what task they did, the brain looked the same. Like 60-some% accuracy versus 98 point something. So that's again where the graph can help you because you can just measure modularity. So again, when I say measure modularity, I don't mean you run community perfection on top of it. Based on the annotation, you can say, if you consider these annotations as communities, then how much segregated they are by simply computing the quality of modularity, not actual modularity. So that gives us segregation information. And that correlates nicely with behavior. And then again, you can go back in time. So we start with 4D data to this compressed representation, then you can go back in time to say whichever TR are either connected and part of the node, or those time frames are connected by an edge. They get a non-zero value in this matrix. Something similar Luke was showing earlier. Yeah, time frame by time frame. So either they're part of the same node, or they're connected by an edge. They get a non-zero value, and it can be weighted however you like. And then you can essentially treat it as a connectivity matrix of itself, connectivity of time. Let's see, different way of connectivity, think of connectivity or recurrence in time. And then if you just treat it like this and measure a degree, how connected each TR is to every other TR, something as simple as that, then we were able to pick out the transitions over time. So points that are highly connected typically turned out to be from the tasks which were highly cognitively effortful, like working memory and so on. We could then pick up these changes in transitions. And then that's Samir and Caleb. Samir is a postdoc. Now he's in an amazing startup. It's one of the problems we have. Awesome people, very, very hard to keep. Everybody has that, I guess, problem. And Caleb is also just graduated, and he and Samir made the dinosaur tool, which you guys can play with today. And Samir and Caleb also made another tool called New Mapper, which is like a scalable mapper. So it can, if you have millions and millions of rows, you can run it like in almost constant time. So you can play with that. But in this movie, this is 1% data, and sorry. the other cool thing is, so because I said like mapper, you can go back to the anatomy very nicely. So this is where the resting. So I'm highlighting TRs here. It's like the TR number. And as wherever that TR is, I'm just saying, okay, show me the nodes which have that TR. And you can see this, you can get this traversal on the manifold. And that's actually very useful because, as you know, that fMRI data is like highly, too much autocorrelation in fMRI data. So then you can kind of see this tail popping up, like this, like a kind of comet, but like a bunch of nodes kind of flowing together. And that property, if you shuffle the entire matrix in time, like in rows, you get the same graph. Because of the fMRI ACS, you can get this beautiful kind of tail-like structure that like goes on the graph. But that's very helpful because then we can get spatial activation, deactivation at the single TR level. So statistically corrected at the cluster level. So typically in fMRI, if you correct anything at single TR, single person level, you get nothing. But because mapper kind of picks up the interesting time windows, so let's say TR 5, 10, and 25 and 71 are highly similar. Now I can use that information to create a GLM for TR, whichever TR I'm looking at, because I know which other time points are highly similar to this particular time point. So that helps me and look at activation, deactivation at the single TR level, making some sense. It kind of gives us a window by increasing the SNR of the data. Yeah, so that's the way. Another cool thing you can do with this, I don't know if I have this in this movie, but then you can basically color the graph however you want, from head movements to all the things. Like I think later on I color the graph by like, so this is like hit and miss. Where do they make error in the trial? You can color it by FD or like head motion. Typically what we find is with the FD, these guys, like this chopping happens because of censoring. So we censor like heavy head movement stuff. So that's when you see this disconnected portion. Yes, FD affects everything, or head motion affects everything. No? Doesn't matter because it's a relation between nodes. The layout doesn't matter. You could, yeah. So you can create the same. So initially I showed that you can, sorry, it's annoying. But in the original, when I was showing the map algorithm, right, I went from like high dimension to 2 dimension. You can go to 3, 4, 10 dimensions, however many dimensions you like to do.
So layout matters, so those are all depends.
Does the relationship between modularity and performance depend on the set of tasks that you use?
I think here we only look at like average performance, but it could matter, I guess. Yeah, I guess.
You have a set of like 5, working memory intensive tasks. Would you still expect modularity to help performance?
Yeah, that's a good point. If you expect that the spatial topographies are supposed to be different, then yes, I would expect it. If you don't, then yeah, probably it's something else. Good point. Yeah. Annotations, not the modularity. Like we didn't run another community section on top of it, right? We just said, I'm going to color it by the task label, and that task label is considered a community. So now just give me the quality of modularity.
You should put it out.
Yes.
When you were showing the brain plots,
yeah.
I guess is that just like the average of the Z-score data?
No, this is every single TR data. It's one person, and then as the like wherever the highlighted nodes are, it's those TRs, and we did a spatial mixture modeling, like a GLM, by saying just give us a. So this was kind of done offline. We done like in real time, but then you just for each TR get this picture and this plotting. But this is done at a single person level.
And the thresholding chart yourself.
Thresholding, we use the cluster correction that FSL has. Like we didn't threshold it. This is like apparently significant family-wise cluster corrected data that you typically see in group, but you could then see as a single TR.
But there's no reweighting with your manifold for the
No.
corresponding.
No, nothing. Just every TR, which TRs are either part of the same node or are connected. I'm going to take all of them rather than taking one TR.
That's how you feel.
Very, very quickly, let me take you through the resting state data because this, well, rest is far from restful, probably. But so we looked at the midnight scan club data where we have, they had collected like 5 hours of resting state per person over 10 sessions. And they had like these individualized networks assigned for each person. And that apparently is a big help. So we saw that, so if you can do individualization in terms of network, I mean, of course, you don't always have to have 5 hours of data. With like half an hour resting state, you can do that too. But if the networks are defined at a single person level, the results are much different than if you take any group isolation. So we again applied, so we did 5 hours of data, we split it into 2 halves, 2.5 hours, 2.5 hours of resting state for validation, like even session versus odd session. And then you get much denser mapper graph because now we have 5,000 points rather than like 1,000 points we had earlier. And again, the points are with the spatial activity much similar, so they're individual timeframes. And now, how do you color them? So there are multiple ways. There's no task, but you can color them by the topology of the graph itself, like high degree nodes, the degree of the graph itself. And we found that there's this fat tail in the degrees distribution in the real data. And this is where we found the PR null and MAR null are actually do a better job in picking up differences. And the idea was that this is average over all 10 people, even versus odd session, and we found this fat tail, meaning there's existence of hub nodes or some highly connected nodes in the manifold that is significant. And these are the nodes that I'm just showing you, roughly in the center of the graph. And I'm going to come back to them because they turn out to be very interesting properties, these hub nodes. You can color the graph also by resting state activation. So within each node, you have multiple TRs, and you can say, just like with the task, show me the TRs that where default mode network is one standard deviation above the mean or something, or where some of the network is above the mean. So then you get this kind of a graph. So if you think of it like a map of US, and default mode goes to Texas for some reason, and then frontoparietal dorsal tension on the West Coast, and where we are right now, I don't know where we are exactly, but we are in the auditory space, and then so on. So this is one person. So every person has a different layout of the manifold, which networks go up. And the cool thing about this method in a way is also that you don't have to have the mutual exclusivity, which you typically have at HMM. Only one network can shine. You can actually look at how different networks can go together. For example, red and yellow and green love to hang out together in this person. But then different networks go up and down. So as you look at the same person data on a different set of sessions, the overall graph doesn't look identical, but which networks hang together is identical or similar. And so then you can again go back to the brain for each network. You can here we didn't even have to do any kind of spatial mixture modeling because the data was pretty dense. We just did average. So if the default mode is majority, you obviously see that on the brain. If some other networks are the majority, you see them on the brain. But the hubs were the most interesting because they didn't care about any particular network, more or less. They were more uniform distributions. These networks that hang together is very subject specific. This is just showing you which networks are going up and down together across different people. And that had much higher within participant similarity. And also you can go back in time using like a winner take all strategy. You can say for each node, whoever is the majority network that wins. So for all the TRs, that network is a winner. And then you can get like a time series of transitions of different resting state networks. And there we found that, and then we assigned hub nodes a hub category because there was no clear winner, which network was the winning. I'm sorry if I'm going too fast, please stop me. And then we could then see that if you just look at the simple Markov chain transitions, like the transition probability from going from one state to the next. Hub was the most sought after transition after every network, meaning if you're on that graph and you have to go from default mode like Texas to California, you have to go through somewhere in the Midwest, the hub nodes. They acted like transition hubs or a central station. I'm not showing here, but we did this in ABCD data set, and we found that these hub nodes, the proportional hub nodes, are highly related to attention deficiency and poor cognitive functioning. So we're writing that up. So hopefully I'll have those results for you guys soon. And these temporal transitions are also highly replicable within people. Okay, good. So I'll end at this one. This is where we looked at the naturalistic data set, which I was showing last time with Sherlock. This is again one-person data, and you can color it however you want. So here you can look at any stimulus property like arousal valence, or in your case, if you may have like, I don't know, skin conductance or like different emotion categories or whatever you have, you can color the graph based on that and look at how, for example, wherever the valence goes up, like the engagement goes up or no, or stuff like that. So interestingly, we found that for this person, valence and recall had no connection, or not significant at least. But valence and engagement was highly significant. So whichever nodes had higher valence, whichever time points had higher valence also had higher engagement. But remember, these graphs were generated from the brain data alone. There was no information. So you're like your meta information weighted by the brain, right? Okay, if no questions, we can go to the demo. No. Confused enough? Cool. Okay, so these are the two links that should be on in the Slack channel. This is like the notebook link. And just go to that one too. So Caleb, my guy, did an awesome job maintaining these, and he's still maintaining the repo. So if you have any questions, feel free to raise them there as well, especially like Python related questions. So this is the toolbox, calling it dinosaur. That's on me. But then he has these small demos as well if you don't want to do the entire notebooks. So he has this way of kind of visualizing, again, the same trefoil knot, but trying different dimensions and showing you each step of the mapper process. You can know how different parameters can change different things, and also applied it to Haxby data, the decoding data. And I think you can even play with, I'll find, so it basically generates this web interface where you can drag your graphs and kind of color them in different ways and so on and so forth. This is the trefoil knot notebook. And it's pretty straightforward. I don't know how much. This is like the simplest data set. We create this trefoil knot like a 2 equation system to that you can generate this 3D trefoil knot. It's just showing you, like, if you imagine trefoil knot as a time series, it looks something like this: the X, Y, Z, assuming them as time in time. And you can visualize in multiple ways. You can look at different orientations of the graph. And then you can try here your favorite, I think it's connected with sklearn, scikit-learn. So you can try different dimensionality reductions, starting from like just letting go of one dimension to trying like t-SNE and all kind of fancy things. And then looking at how the mapper in Python, in MATLAB, we have our own mapper version, which is very similar to this Python version, which is called K-mapper, Kepler mapper. It's an open source mapper toolbox, which can then kind of try to fit the data. So here you can visualize every single stage of the mapper as you change parameters, and you can see how the green points get more clustered with themselves than with blue and red points. So you can kind of separate them out. And then if you just change the layout, then you can capture the shape, which is matrices of them. Sorry, that was too fast. Any questions?
So is that possible to in one?
We can go from any D to any D.
So if one is similar.
Yeah, I mean, that's why the notebook, go play with it. Most likely in 1D, I don't think you will be able to capture the closed loop. For the loop, you need to have 2Ds.
Yeah.
But yeah, you can do anything. It works. Actually, I tried running it. It's working. And then the other one, so is the trees for.
It depends on. So this is.
Yeah, actually, I have an example to show that. It's a good point. I'll show you an example for the. Yeah, let me just go through this and I'll show you an example of how using UMAP versus TSNE versus PSQ and Haxby data separates the data set more. Yeah, I'll show you in a second. But so here in this case, Caleb used so the K-mapper dinosaur stuff is the same as earlier. He's using NILearn to load Haxby data, which is already pre-processed and it's available to play with. And then again, you can visualize the heck out of it. And then these are like the different, this is like the meta information, like showing scissor versus something else. I think this one is like whatever they were trying to show, like all different objects. So that's the meta information you will color it with, which time point of which object or category. And this is a entire piece of code from like loading the data to running Kepler mapper and then creating a graph out of it, which should have popped up somewhere here. Okay, so one thing I could not make work was it's supposed to create like an in iframe HTML inside the notebook, but somehow that maybe Jeremy can help with, but I couldn't figure that out. Not that good at Python, but not good at all. But this is Haxby data, and you can kind of drag drop to whatever, and then you can choose. We love dark mode, but fine, no white. And then you can choose different layouts. You can choose. You can play like a movie. You can choose how do you want to color it. You just want to know where cat is. This animation is how you get paper published. Cool animation. Nothing to do with anything. This is like scissor versus everything else. Space is like living here in the space somehow. So like one shot coding of like where is chair versus like 1 versus 0. You can also color it by different resting state. Oh, this is 0 and 1. Like this is fixation versus looking at this, doing that. Apparently that's also separated on this particular person. And then you can just play it like a movie if it works. Yeah. So if it was resting state data, nicely sampled, you could see very nice traversal on the manifold, which in this data, you don't have enough points to see it. And it's also only looking at the ventrotemporal cortex rather than the entire brain. Cool, and now let me find that link that you were talking about. So if you look at, let's say, Caleb is so nice, he just made these, so I don't have to do much. This is TSNE versus UMAP versus, apparently there's something called supervised UMAP. So again, the same Haxby data. This is with UMAP, so it has much nicer separation. So these are the parameters you have to tweak and play with. For the data for resting state graphs, we found isomap to do the best job because UMAP its own hyperparameter and just tweaking them takes forever. I stayed away from it. This is supervised UMAP, which is like, I don't know, UMAP on like Red Bull or something. It does a pretty good job of separating. Do you know supervised UMAP? Yeah, maybe somebody here knows. Oh. So apparently it's like too good. Nothing against UMAP. Like And then this is, I think, the T-SNE version. So this is T-SNE versus UMAP. UMAP is certainly giving, so this, I think, is resting state, if I'm not wrong. So UMAP is parsing the resting state more. So UMAP is apparently doing an interesting thing where it's separating the rest from the task more. But if you look at T-SNE, or maybe both are doing it, it's possible. Yeah, never mind, both are doing it. But somehow the T-SNE is giving you more separation here. So these are the parameters you kind of have to work with and show that your results replicate and blah, blah. You can take them back to the brain and find something cool. I think maybe Jeremy was mentioning yesterday, like you make a cool tool and then you have to show some cool neuroscience results. So that's too much. Make a cool tool should be enough. You go find some cool neuroscience. You know. That's it. Yeah.
Curious, how do you deal with the multi-site? Like with them, you like concatenate the
Multi-what, sorry?
like multi-subject.
Oh, so yeah, so we in this, everything is single person right now. Everything is done at a single person level in the SIFT, either the SIFT space, like the gray ordinate space, or parcellation, individualized parcellation. And then the graph properties, you can look at the multi-subject level. So that takes care of the alignment.
And try.
We tried.
On the graph.
We did.
It's like a graph type of one.
Yes, there's the big graph correspondence problem. Like you can, so if you're not doing the time wise, if you transpose the matrix and you're interested more in like how regions are similar to each other, then it's much easier. Because there is a one-to-one mapping. With time, there is not a good way, especially if it's resting state. But there is apparently a graph neural network toolbox which can give you a graph correspondence for each node. So you can align them. We never touched it. It's too much, but it's possible.
I have a question unrelated to this, but back to your original talk where you mentioned you had results on creativity, like you were able to make people more creative. I was just wondering how you did that very briefly. Like,
oh yeah, so we that was like a very crazy project, but Stanford has this thing called design school, where one of the teachers, Grace Hawthorne, used to teach a course called Creative Gyms. The whole point of that was by teaching people design thinking principles, they can be better at thinking outside the box, definition of creativity. And so she approached Aaron, my boss at the time, saying, can we test it scientifically? And so that's what ended up being the study where they was like 10 or 5-week course, something like that, where each, I forgot how many days, but each day they would get like 2-hour classes of things like bias toward actions. Like if you have a problem you don't think you just do, or you have a fail fast methodology, stuff like that, where the whole point was making people do more and think less, like get rid of and prototyping, all those things. And we tested it by how do you test the thing? And that kind of somehow fell on me. And that was a crazy idea. Then I love Pictionary. All answers to my problem is let's play Pictionary. And that worked. So we asked them, we didn't tell them to be creative inside the scanner or anything. We just said, go play Pictionary. And later on, we took these images to people and said how unique, because for each word, you can have any kind of drawing. So how unique each drawing is as compared to the entire sample, like the frequency, and how easy it is to guess the word. So utility of the product and how unique it is, get the creativity score. And then we later on saw that their creativity on the game went up, and also Torrance test of creative thinking is out there, which tests regular creativity, but that also significantly went up.
as we're talking here, I would have thought you could give people like tools for creativity, right? Like simple operations that you could use to like be more creative in general. So for example, as I'm thinking here, I'm just thinking of a few that I guess I use. Like one is like combine, take two things and combine them, what comes out.
Yeah.
Another is flip, take something and make it inverted, what happens there.
That's actually one of the.
Another is leap, move through the conceptual space completely in a different direction or spot. So just like 3 things.
Yeah, that's a great point. I think Grace had like similar things, but the difference was they were also like the D school thing is like also like doing with playing with things rather than sketching, like they would have like these. What do kids play with Play-Doh and stuff like that? So Yeah, like for example, one of the things that your flipping reminder will flip 180. So if you're trying to make a chair to sit, try to make a chair to stand, like things like that, you flip 180 the problem, or you don't think and do, or you show that everybody's dumb, you're not the only one. So that boosts confidence apparently.
Because that's like your TDA thing. It like looks like you flipped it. You literally just take the matrices and flip them on their head, right? Like 90 degrees. And it's so cool.
Apparently it works.
So cool.
Eventually I'll succeed. Cool. Go play with it. Yeah, play.